Hello and welcome to this introductory video on Dijkstra's algorithm. This video will give you a very intuitive understanding of how Dijkstra works and why we use it. Let's start with a simple real-life example. Suppose you want to travel from your home to several different locations in the city. You need to choose the best possible route, and that best route always comes with a price we call cost. Here, the cost is simply distance. The shorter the line in meters or kilometers, the better the route. But sometimes the cost is not about meters and kilometers at all. It's about time. Now look at this second route. From home to the drugstore, it would be very easy to drive almost straight across the city. But imagine there has been an accident or some roadworks, and that direct road is blocked or very slow. In that case, the shortest path in distance is no longer the best choice. The navigation app changes the route and sends us on this longer-looking blue path because, even though we drive farther, we arrive sooner. Note that Dijkstra's algorithm doesn't know about accidents directly. It just takes the updated costs and finds the path with the smallest total cost, whether that cost is distance, time, or something else we choose. Now let's look into an example. We have 5 locations, A, B, C, D, and E. Each white line is a road, and the number on it is the cost of that road. Our goal is to find the cheapest way to reach every node starting from A. We start Dijkstra's algorithm at node A. On the right, we have a table that will store, for each node, the best cost we currently know and which previous node we came from. At the bottom, we have a priority queue. This is where we keep all the nodes that are waiting to be processed, and they are always processed by their current shortest cost. Because we are already at A, the cost to reach A from A is 0. We don't pay anything to get there. So in the table, we record that the shortest path to A is 0 and its previous node is empty or none. Before continuing, let's take a closer look at the priority queue. In a priority queue, we have 2 main operations, enqueue or insertion and dequeue or removal. Here we have 3 elements, A, B, and C. Each one has its own cost, and this cost becomes its priority. The important idea is this. The element with the lowest cost is always processed first, no matter when it was added to the queue. It doesn't matter if it's the newest element or the oldest. What matters is its priority value. In this example, A is processed first because its cost is 0. Then, between B and C, we process C because its cost is smaller than B's. This shows that in a priority queue, the element with the lowest cost is always handled first, regardless of when it was added. Let's continue with our example. We have already processed node A, but for all the other nodes, the algorithm still doesn't know the best way to reach them. For example, here, there might be more than one way to reach B from A. One option is to go directly from A to B. Another option is to go from A to C and then D to B, which might actually have a lower total cost. This is why the algorithm has to explore different paths first. Dijkstra now needs to explore the graph to discover the best possible cost for each node. For every node other than A, we write an infinity symbol in the table. This simply means, for now, the cost to reach this node is unknown, or we can think of it as extremely large until we find a better path during the exploration. Now it's time to put all the adjacent nodes of A into the priority queue, so we can start finding the best routes from A to its neighbors. Node A has 2 adjacent nodes, B and C. Reaching C from A has a total cost of 1, and reaching B from A has a total cost of 5. These values are both better than infinity, which we used before. We now insert all the adjacent nodes of A into the priority queue. This allows the algorithm to decide which node will be processed next based on their current cost. The node with the smallest cost in the queue will be chosen and processed first. Now we update the table. The cost to reach B becomes 5, and the cost to reach C becomes 1. These are the best costs we have found so far for those nodes. To build some intuition for the table, think of it this way for this row. The first column, namely node, tells us which node we are deciding to reach. This is like our destination. The middle column, namely shortest path, tells us how much it costs to reach that node from the source node. The third column, namely previous node, tells us where we come from to get that best cost, and you can think of this as our source node. So based on the current costs, we see that C has the smallest value. We now choose C as the next node to process. At this point, A is fully processed, and there is no reason to return to it anymore. We say that A is visited, meaning its shortest path is final and will not change. Now we look at all the adjacent nodes of C. Its neighbors are E and D. Since we have reached C with a total cost of 1, reaching E from C now costs 10, and reaching D from C costs 2. Both of these values are much better than the previous infinity we had for them, so we update the table and the priority queue accordingly. Now we insert these adjacent nodes into the priority queue so the algorithm can decide which one should be processed next. You may have noticed that there is still an older element in the priority queue that hasn't been processed yet. A node stays in the priority queue until one of two things happens. First, it is selected, meaning it becomes the smallest cost node and gets popped for processing. Or it becomes stale, meaning a better cost for that same node was discovered later, so when the old entry is popped, it is simply ignored. Among all the elements currently in the priority queue, D has the smallest cost, so we choose D as the next node to process as C is already processed. Now we've reached D, and it becomes our current node. Since the total cost to reach D is 2, we now look at all its adjacent nodes. From D, reaching those neighbors gives us better costs than before. Therefore, we update their values in the table. This means we've found smaller and more accurate costs for those nodes. Now we push the adjacent nodes of D into the priority queue. The new values for E and B are both better than the older values we had earlier. With everything updated, we can now compare all the elements in the queue and decide which node has the smallest cost. That node will be selected next for further processing. Now we select B because it has the smallest cost among the remaining elements in the priority queue. We mark B as visited. At this point, we can also see that B has no unprocessed neighbors, so nothing new needs to be updated. After popping B, we look again at the queue and notice that there is still one unprocessed node left, and that is E. So we select E, mark it as visited, and with that, the algorithm is complete. You might still see 2 old items left in the priority queue, but we don't use them anymore. They're just outdated costs that stayed in the queue, and the algorithm simply ignores them. Now let's see how this table actually helps us. Suppose you want to travel from home to your final destination, which in our example is node E. Start by looking at the row for node E. The table tells us that to reach E, we should come from D. So now look at the node column again and find D. From the table, you can see that the best way to reach D is by coming from C. Next, find C in the node column. The table shows that to reach C, we should come from A, and that's it. We've reached the starting point. So the final path is from A to C, then C to D, and finally D to E. Now that we know the best route, you can start traveling safely. I hope this video really helped you understand the intuition behind Dijkstra's algorithm. Feel free to share your thoughts in the comments, and if you found it helpful, please support the channel by subscribing and sharing the video. Thank you.